Welcome to my talk, and thank you very much for the previous speaker, Vladimir Erokin, for the very good introduction or very good explanation on the calculation that was performed on the triplet states of helium. So this gives me a good introduction to my talk, where I will talk about manipulation of metastable helium atoms in the triplet 2s state, which we want to do for high resolution spectroscopy. So I think my introduction is a bit superfluous because you heard everything before. But so we want to perform high resolution spectroscopy on helium atoms because this is the simplest 2-electron system, because it has no hyperfine structure because of the nuclear spin of 0. So throughout my talk, I will use these energy level diagrams where I display triplet states on the right and singlet states on the left. And they are ordered according to the orbital angular momentum quantum number. So as you just heard, there was exactly a year ago, the first calculation was published on the QED expansion term of helium, including the complete treatment of the alphas to the power of 7 correction term. And here you can see such an expansion in terms of the fine structure constant alpha. And so what was found that with the relative precision of 4 × 10⁻11, they were calculating the level positions of the triplet 2s and triplet 2p state very accurately. And then they could, before our measurement was published, they could already compare with existing transition frequencies which were measured beforehand. And what was found is there was a good agreement between the transition frequency determined experimentally and theoretically for the 2s to 2p transition. However, there was a very large discrepancy between the experimental and theoretical transition frequencies determined for the 2s to 3D and also for the 2p to 3D transitions. So we contribute, So there was a first attempt already in trying to resolve these discrepancies by in an article from Zaliali-Dunov and co-workers, where they looked at non-resonant corrections, which might be responsible for maybe problems on the experimental side, where quantum interference effect might shift the transition frequencies. However, they already included that with these, with the inclusion of the quantum interference effect, they still cannot find, they still cannot eliminate the current imbalance in the study of helium spectra, and the question is still open. So, and this question needs to be solved such that fundamental physical constants as the alpha particle charge radius can be determined in the future. Okay, so yeah, I will talk now quickly about the measurement which we have performed, where we try to contribute to this puzzle with the measurement of the ionization energy of metastable helium atoms in the singlet 2s state, which we did through Rydberg series extrapolation. So the way our measurement works is that we measure transitions connecting the singlet 2s to the NP Rydberg states, and we measure a series of different transitions such that we can then extrapolate to the ionization continuum. And then combining our result for the ionization energy of the singlet 2s state, we could use a whole thermodynamic cycle to extract ionization energies also for the triplet states. And this was done using also the measurement for the triplet 2s to singlet 2s transition measured in Amsterdam. So, I mean, this was mentioned before, but we could then directly compare ionization energies instead of transition frequencies between the triplet 2s and 2p state with the theory, and also between the triplet 3D and singlet 3D states. And as was mentioned, there was a large discrepancy found of almost 400 kilohertz between the triplet 2s and 2p state between experiment and theory. However, there was a good agreement for the ionization energies of the 3D states. Okay, so I will give you a few words of introduction into how we perform our measurement. So this is a typical spectrum, what in this case was measured to the ATP Rydberg state. And our spectrum consists of 2 peaks, which come from 2 Doppler components. Because the way we did the spectroscopy is we use a laser beam, which is at near right angle crossing the atomic beam. And then it was retroreflected such that the first order Doppler effect could be cancelled as could be found as the average of the two Doppler components, so that we can find the zero Doppler shift position. And our spectra have a line width of 4 megahertz, which resulted from Doppler broadening. Okay, so I will also explain you the. Yes. So the question was if we intentionally misaligned the laser beam. Yes, so we have the laser beam at near right angles, but we intentionally introduce an angle such that with the retroreflection we get the Doppler shift in the opposite direction, so we can resolve two Doppler components. Okay, so I will quickly introduce here our error budget of the last measurement so that you also have an idea of what can be improved in a future measurement. So we considered a list of systematic uncertainties and also looked at the statistics of our measurement. And for the systematics, we looked at the pressure shift, a DC and AC Stark shift, a second order Doppler shift, and a photon recoil shift. Now, the biggest systematic uncertainty was the frequency calibration, which resulted from referencing our laser to a frequency comb that is referenced to a GPS rubidium clock. Then on the statistical side, we got a statistical error of 25 kilohertz, which was a combination from the line width from the Doppler broadening and also the residual first order Doppler shift, which could not be cancelled. So these two effects, the frequency calibration and the Doppler broadening, are two things what we want to improve in our future measurement. Okay, I will show you here our experimental setup. So the idea is that now we want to measure the ionization energy of the triplet 2s state directly and not go via the singlet 2s state. And there are a few, so the first part of my talk is, the main part of my talk is introducing to you how we can improve the Doppler broadening of our spectroscopy. And we plan to use a combination of two experimental methods called Zeeman deceleration and laser cooling, because our atoms in the triplet state have two experimental advantages to us over the singlet state, because we have a electron spin of 1, which enables us to use the magnetic moment of the atoms. And also in the triplet state, we find a closed laser cycle transition. Okay, so let me explain you the experimental setup. So here on the bottom, you can see our sketch of the vacuum chamber, where on the left, we first create a supersonic expansion, so a pulsed supersonic expansion of helium atoms, which are then excited to the metastable triplet state in a dielectric barrier discharge. The atomic expansion goes in this direction. And so we first use a Zeeman decelerator, where the goal is to decelerate the atoms such that we can reduce the longitudinal velocity. And then we have a laser cooling section where we can recollimate the atomic beam. And this is important because we perform our spectroscopy here in the spectroscopy region, which is happening with a laser beam crossing our atomic beam at right angles. So the opening angle of our atomic beam actually defines our Doppler broadening of our spectra. Okay, and then for the frequency calibration, I will not talk a lot about this. So we plan now to lock our laser to a ultra-low noise frequency comb that itself is referenced to that itself is now SI traceable via a fiber link to the Metrology Institute in Switzerland, METAS in Bern. And Zeeman explained this to you yesterday. Okay, and I think I forgot to mention one thing about the spectroscopy. What is important for the next slides is that the way we detect our atoms is we drive transitions to Rydberg states, and then we can pulse field ionize our Rydberg states and extract the ions towards an MCP such that we can detect them. And this is important to know. So here you can see a cross-section of our vacuum chamber, where we have here the cryogenic source, which is cooled to liquid helium temperature. So we have an initial velocity of 500 meters per second in our atomic beam with the discharge electrode. Then we have a Zeeman decelerator and the laser cooling section. And the Zeeman decelerator not only decelerates our atomic beam, it also separates the triplet component from all the remaining part in the atomic beam. Then we have our laser cooling section, which will be used to refocus the atomic beam, and here the excitation region for the spectroscopy. Okay, so the next few slides are about the Zeeman deceleration. So I assume a few of you are not familiar with the concept of Zeeman deceleration. So the Zeeman decelerator uses inhomogeneous magnetic fields to decelerate atoms. And the force on an atom, the force resulting from a Zeeman effect on an atom in the triplet 2s state is shown here, where the force is proportional to the gradient of the magnetic field. So in our case, we can decelerate atoms which are in a so-called low field seeking state. So this means that their potential energy increases with decreasing magnetic field. So for the Zeeman deceleration, we use a series now of 30 coils, where coils are so-called solenoids, which are displayed in a row, and we can pulse the magnetic field inside such a coil. So now what we do is we switch off the coils according to a certain position when the atoms are in a certain position in the coil. And this position we call the phase angle. So an atom which is in the center of the coil, we would call the phase angle 90 degrees. And the switching off enables us to remove the potential energy from the atoms in each deceleration coil. So we remove kinetic energy. And if we do this in a series of 30 coils, we can then, in theory, we can bring a whole atomic beam to rest. Okay. So I will now explain you a bit the influence of the phase angle for which we choose to decelerate our atoms. So here you can see a cross-section of a magnetic field in such a coil, not only in longitudinal direction, but also in the transversal direction. And you can see that there's a saddle point in the center. So this means that our low field seeking states, we cannot only decelerate them, but we can also create a focus of the low field seeking state towards the center of the coil when our atoms are approaching the center of the coil. I mean the longitudinal center of the coil. So this means that we can define a trade-off between different phase angles by choosing a deceleration sequence. And the trade-off is either we can use very high phase angles, which will lead to also focusing our atomic beam back to the center, which is good for stable deceleration. However, in this case, we might lose a few atoms which are faster because they might have already passed the center of the coil and accelerated again. Or we can choose a low phase angle, which means that we switch off the coils way before our atoms have reached the center of the coil so that we create more longitudinal phase stability. Okay, so this is a first spectrum of what time of flight spectrum of our experiment. So what we did in order to record the spectrum is we delayed the extraction of the ions generated by the pulse field ionization with respect to opening of the valve. And here in blue, you can see a trace of just the normal atomic beam, which is not decelerated, which has a velocity of 500 meters per second. And in red, you can see the corresponding time of flight spectrum when the decelerator is turned on to decelerate up to 300 meters per second. And you can nicely see that this peak corresponds to the low field seeking states, and this part also a bit, which is but not phase stable. And here you find also a little bit of accelerated atoms, which might be the high field seeking states. Exactly. So with this time of flight spectrum, we could then optimize the deceleration sequence by finding the most probable beam velocity and also a good incoupling time for our decelerator. Okay, so now one more idea is with using the decelerator is not only to decelerate the atoms, but maybe we can increase our whole intensity of our setup by using a focus when using the Zeeman decelerator. So the idea is that the Zeeman decelerator will not only be used to decelerate, but also to create a transversal focus. But the focus, I mean, as I told you before, we actually do not necessarily want, because this would imply that we increase the transversal velocity spread, and we have very broad spectra. But with the laser cooling section, we can then recollimate the atoms which are focused so that we have a dense and collimated beam. Okay, so the way we think we can do this is by using a sequence for deceleration which is split into two parts, where the first part is only used to decelerate the atoms with a low phase angle. And then we choose a few more coils where we use a very high phase angle just to create a transverse focus. And now to think of the focus, we have to think of a phase-space diagram so that we can find out if it is possible to do so. And a phase-space diagram is a diagram where we plot the transversal velocity with respect to the transversal position. And the focus means that we need, after the deceleration process, a negative gradient in such a phase-space diagram so that with the time evolution, the atoms can then travel to the center, and we have a position, which is this line here, which would exactly give us a focus point where our atoms are all in the same point, but they have a different transversal velocity. Okay, so we tried to figure out with the Monte Carlo simulation if this is possible. So we simulated a sample of atoms that are going through the decelerator. And just after the deceleration process, using this sequence, we actually managed to find such a negative slope in the phase-space diagram, which in the focal plane then looks like this. And after the focal plane, it will just evolve further as a sort of elongation of a phase-space diagram. And this is a cross-section of how the cross-section of our atomic beam looks like in the focal plane. Okay, so now I will focus on the laser cooling part. So we use laser cooling with the so-called optical molasses. And I will firstly give you an introduction of what are requirements for us to perform laser cooling. So of course, we need enough laser power in order to be able to saturate our transition so that we can cool efficiently. Now we need a laser cooling transition that itself has a very high spontaneous emission rate so that we can scatter efficiently and have a lot of scattering processes. But also the spontaneous emission rate is proportional to the Doppler cooling limit. So we don't want it to be too high so that we can also reach very low temperatures and have a very collimated beam. Of course, we need a closed optical cycle transition such that we do not lose our atoms in the laser cooling process. And we need the tunability to match the Doppler detuning. And let me quickly introduce you what this means. Well, such a process would look like, so we have an atom which is traveling at velocity v, and we have the photon coming in with the momentum h/k. So upon absorption of this photon, the velocity is reduced to v minus h/k over m. And then the spontaneous emission is happening in a random direction, such that when you sum up a lot of these processes, we'll get a force resulting in the direction of the laser beam. But in this case, what happens is that the velocity of the atom changes with each scattering process. So we need to be able to find a way to match this Doppler detuning. Now, a few words about the helium atom laser cooling transition. So we choose a transition connecting the triplet 2s to triplet 2p, which forms a closed cycle where we use a j equals 1 to 2 components. So the Doppler cooling limit is on the order of 39 microkelvin, which corresponds to 0.28 meters per second transversal velocity, and this is quite low. So this would be a very good goal for us to achieve. And then also the velocity change upon one photon absorption is only 91 millimeter per second. So we need a lot of scattering processes such that we can laser cool efficiently. So this is a setup of our cooling laser, where we have a fiber laser that is amplified to 3 watts and then distributed to 2 parts connecting to the laser cooling in the vertical and in the horizontal direction. And this part is about the locking of the laser, and we use saturated absorption spectroscopy to lock our laser to a line of metastable helium, to just a normal transition. And this box where we do it, it's a RF discharge box where we have our atoms now here in the metastable state. This is why you see the nice blue glow. And we use an EOM to modulate the frequency of our laser beam before doing the saturated absorption spectroscopy, so that we can use a Pound-Driver-Hall method to lock our laser with the transition. One more thing, what is very nice, what we introduced is two Helmholtz coils, which create a magnetic offset field in the center of these of this box, so that we can also offset our laser cooling transition with respect to the atomic transition and introduce a detuning. Okay, so now about the laser cooling, we use a so-called tilted mirror approach, which okay, I will explain to you here. So we assume that our atoms, before entering the laser cooling section, have a Gaussian distribution of velocities. So now what we have to do is, or in this approach, we use a set of mirrors that is retro-reflecting the laser beam. And upon each retroreflection, the angle of incidence of the laser beam with the atomic beam changes. So this means that we are now resonant with a different velocity class of our atomic beam. So in the beginning, we have the biggest angle of our atomic beam and laser beam. So we are now resonant with the fastest transversal velocity atoms. And throughout the laser cooling process, this angle decreases. And at the end, we are at near right angles, so that we are now on resonance with the atoms which are almost collimated. And this approach was developed by the Wallraff group at ETH Zürich, which we could thankfully take over. Good, so this is a few small calculation of a small estimation of how this laser cooling process would work. So what we try to calculate now is the resonant transversal velocity of our atoms with respect to the laser beam at a certain number of reflection. So in the beginning, as I told you, we are now, for a certain geometry, we are now resonant with the largest transversal velocity. And then throughout the process of laser cooling, this will decrease. And in the end, at the almost at the end of the mirrors, we are now resonant with a very small velocity. So with our detuning of the laser beam, we can choose a blue or red detuning, such that if our alignment is not perfect, we can compensate for the fact and also still be able to cool. Okay, so now what we used is an MCP, an imaging MCP, such that we can record images of how our atomic beam looks like throughout the laser cooling process. So the first image, so in red, I have marked the border of the MCP. So the first image shows you how the atomic beam looks like when we have only used the Zeeman deceleration, but did not apply any laser cooling. And you can see it spreads out almost over the entire range of the imaging MCP. Here, the second picture shows you a 1D laser cooling. And then with the last picture, you can see how actually how the cloud is cooled. And this is an image of the cross section, which we fitted to around 8 millimeters. Good. So, I mean, we are interested in the spectroscopy. So thankfully, I can show you very few, very preliminary spectra, which we just recorded last week. But please take care that this absolute scale here, you cannot take now as reference, because we only referenced our laser to a wave meter, not to a frequency cone yet. So the first part here shows you a spectrum where I want to show you how we can enhance our signal intensity upon using the laser cooling, where in blue, we did not perform any laser cooling to record the spectra. And now in red, we can we use the laser cooling. Then also, so as you notice, the line width doesn't really change. And this is due to the fact that our opening is still smaller than what is the smallest of the size of the atomic cloud after laser cooling. So this is the reason why the line width doesn't change, but the intensity in the center increases. Now we also use the Zeeman decelerator in combination with the laser cooling to demonstrate that we could already decrease the full width half maximum line width of the line to 4 megahertz using the Zeeman decelerator. So this was a reduction of almost a factor of 2. Okay, so to summarize, I wanted to show you that this method for combining Zeeman deceleration and laser cooling works to manipulate our atomic beam, that we can then use it for direct measurement of the ionization energy of the triplet 2s state. Now, in the future, we have to further test the limit of our laser cooling with the decelerated atoms. Then what we have to do is now we have to choose a final schema that we can insert before our spectroscopy region so that we can actually select an even further smaller transversal velocity component so that we can reduce the line width further. But this is now we have to weigh it up with the signal strength. Then we have to actually lock our laser to the ultra low noise frequency comb that we can perform spectroscopy and also take care of electric stray field cancellation. So thank you very much for listening, and also thank you to my research group.
Questions? Paolo?
Thank you. Thank you, Gloria, for a very nice talk, and congratulations for the results of the laser cooling. Just a question, what is the limitation to 200 meters per second you were showing? Can't you go lower with the deceleration?
I think with the Zeeman deceleration, we demonstrated already to go to 150 meters per second. So the further you go, it's more crucial to have a very stable, phase-stable deceleration sequence. So one needs to optimize it, and you just lose more and more particles if you decelerate further. So it's,
sure.
I mean.
So you're close to the limit already. Yeah, 150 meters.
I think it was demonstrated before that they can decelerate lower. So I think with further optimization, maybe 100 meters per second would be the ultimate goal. I think decelerating lower, there you will not have so many advantages over the loss of signal strength.
Thank you. Thanks a lot.
Yeah, this is a great experiment. I imagine that this Zeeman deceleration is really violent magnetic fields shaking in your lab all the time, right?
Yes.
So what will be, I mean, how can you shield this in the end to do precision spectroscopy, or what are you expecting as a systematic error from that?
So we have in our system, we have 2 mu metal shields that we plan to, So here you can see 2 mu metal shields which shield our spectroscopy region. And also what you have to notice is that the Zeeman decelerator is turned on almost, I think, 500 microseconds or even longer before our atoms enter the spectroscopy region. So the magnetic fields should have been declined by that time where we perform our spectroscopy.
Okay, please.
Maybe a stupid question, but why can't you use the normal Zeeman slower scheme? Where you have a continuous gradient of the magnetic field and you go through it?
Yeah, this is, I think, also a valid approach to perform experiments. So this Zeeman decelerator is nice because it is it's a deceleration process where you can also decelerate atoms or molecules which do not have a closed laser cycle transition. So for helium, we could use the Zeeman slower, but the Zeeman decelerator, which we have in our lab, is nice because you can also decelerate other species just with the magnetic moment.
Piotr, Grzegorz. You'll be next.
Hi, thanks for the talk. I was wondering about the impact of the transverse cooling on your actual spread of the velocity, and will it impact your accuracy later on the second order Doppler effect, because you had some uncertainty there, although it's really small?
So I think the second order Doppler effect for us is mostly determined by the difference in longitudinal velocity, and this is very negligible, so we estimated it to be below, I think, 150 hertz in our case. However, I mean, one thing you have to take care of when you perform the laser cooling is that you, of course, you change the transversal velocity distribution of your atoms. So I think you have to take care that you do sort of symmetric cooling, that you really just compress and not push the cloud in one direction. However, the way we want to perform spectroscopy is to then measure two Doppler components where the shift would then also, cancel out if you measure in 2 dimensions. But it's important to keep a very balanced laser cooling such that your spectra are also symmetric, because otherwise you will not be able to fit this.
So there's no too much loss, basically, due to this new addition of cooling. Because basically you might distort a bit your velocity distribution in the longitudinal distribution. Maybe you show it in one of the slides. I was wondering if there was some distortion because of the addition of the transverse cooling, that maybe then maybe to the recall or whatever happens, and your longitudinal velocity are no longer coming in the same way as before.
Longitudinal, you mean?
Yeah, but it's fine.
I think that is, we didn't consider this effect, but I'm also not sure if it will play a role, because before we already decelerated and changed the longitudinal velocity on purpose.
Thanks.
Could you say what is the transverse temperature before applying the cooling, the laser cooling?
Before, so I think it's around 5 to 10 meters per second.
Okay, I see.
Because I mean, this is purely determined from the skimmer size, what we choose before the Zeeman decelerator. And I think in our case, the ultimate limit is given by the cross section of the Zeeman decelerator. So this is.
Is there any hope to apply the cooling in the axial direction, longitudinal direction?
Well, I think
like the laser power is too small, or the scattering rate is too small.
So I mean, as I mentioned before, for Zeeman slower, this could be different experimental setup, but we chose the Zeeman decelerator for changing the longitudinal velocity.
Let us think again. Okay, last question.
Thanks. In the Garching measurements of 2S to 4P, 6P, and so on transitions, also with one photon transitions with a retroreflector, there's a huge or significant systematic effect because of this retroreflected laser beam, which is like gives rise to some photon recoil of the spectroscopy laser beam. Have you considered this as well?
Yeah, so I mean, the problem with our frequency is that we cannot use the fiber retroreflector as used in Garching, because for 260 nanometer, there are no such lasers which are available. And I think then you have to estimate how large this effect is affecting the spectroscopy in this case. Okay. Yeah. I think this you have to calculate how much this would impact our spectroscopy. Also I think we do not use a lot of laser power because this transition does not require a lot of laser power. But yeah, I'll
like the natural line width of the Rydberg transition, the lifetime up there is like really long, so you don't scatter that many photons because you have a natural line width of some kilohertz. And I think the light force is proportional to the natural line width.